Heat stress is one of the three really big abiotic stresses that we experience in Australia, and all three have a very big impact on crop production in Australia. Heat stress is up there with drought and frost. There's been a bit of work in the past done on quantifying the extent of heat stress on crop production, and I've got a couple of examples up there. The first one is from a controlled environment experiment where they showed a 3 to 5% reduction in yield for every 1 degree increase in average temperature over 15 degrees. So very quickly would add up to a very significant yield loss. The second is from data from some colleagues of mine where they showed in field conditions 190 kilogram per hectare loss for every 1 degree rise in average temperature. So once again, it's going to add up very quickly and produce some very big yield impacts very quickly. So how does heat affect the plant? There are a number of ways it affects the plant. One is it affects the leaf. The leaf senesces, haze off, the tip burns off, and in wind it can shred as well. So that's what those pictures there are showing. And the reduced leaf area, reduced leaf chlorophyll, reduces photosynthesis, so there's less energy produced by the plant. During flowering, if there's a heat event, it'll burn off the anthers, so that reduces seed set. And there's evidence to show that heat stress also reduces the period of which grain has to fill, so that reduces grain size. And all of those traits all end up to reduced grain yield, so reduced bottom line for farmers. Heat stress is a very big, widespread problem. There probably isn't an area in Australia that doesn't experience it to some degree. And here is just a small data set of showing the extent of heat stress last year. So those are the 4 locations where I run experiments: Roseworthy, Narrabri, Yanco and Merredin. And the number of days over 30 degrees Celsius, so a minor heat stress event, and days over 35, so a more serious heat event. And the range from at least 7 up to 13 days over 30 and this is during the more sensitive flowering grain field period. And 30 days over 35, there was at least 1 or 2 days over 35 degrees at all of those locations. So it happens, and last year didn't really seem like a really hot, stressful period, but it seems to happen every year. So the projects that I'm in charge of, firstly a SAGIT, South Australian Grain Industry Trust funded project where we run controlled environment experiments out at Roseworthy where we look at assessing the heat stress tolerance of current varieties. We also screen mapping populations to dissect the genetics of heat stress tolerance, and we also screen exotic introductions to see if we can find new sources of genetic variants to hopefully regress into germplasm. The second is a GRDC funded heat stress tolerance project where we use the managed environment facilities at Merredin, Yanco and Narrabri, and this is really field validation of the controlled environment experiments and to characterise varietal responses in field-based conditions. So the heat chamber, this is the contraption that I use at Roseworthy to screen for heat stress tolerance in a controlled environment. So we set up our experiments and then we monitor their maturity, and 10 days after the main tiller reaches anthesis, we put the plants into the heat chamber at 36 degrees with 40 km/h winds for 8 hours a day. So it's a very serious, very severe heat stress event that those plants experience, but those events to that severity do occur in South Australia. And we make sure the plants are well watered to remove any confounding effects of drought. Drought can be very closely related to heat, and they can co-occur, but we really want to just dissect the effect of heat stress tolerance without drought confusing the situation. And some of the things that we monitor are leaf chlorophyll, leaf damage. We measure spikelet fertility, so the number of grains produced per spikelet, harvest index and 1,000 grain weight. And all of those treated plants are then compared to an untreated control to really understand the effect that heat has had on those plants. So here is some early data that I produced a few weeks ago showing how fertility is affected by heat and also 1,000 grain weight over a range of growth stages. So when we put the plants into the growth chamber, the main tiller is 10 days after anthesis, but all other tillers on that plant are then tagged with with their growth stage, so we know at what growth stage they were heat treated. So we can then produce graphs like this. And on the fertility graph, it shows that at the earlier growth stages leading up to anthesis and during anthesis, at the late 50s and mid 60s for the Zadox growth stage, that fertility is very severely affected and reduced. And at the later growth stages, once seed set has occurred, there is virtually no effect, which I guess makes sense. 1,000 grain weight showed a very different relationship where earlier on, where there was a reduced fertility, there was less grain to fill, and it appears that the plant was able to fill those grains really well and produced a superior 1,000 grain weight. And at the later growth stages, the heat seems to shut off the growth and reduce the 1,000 grain weight. And those graphs there are mapped as a percentage of the mean of the control. So some more results so far. Those graphs of fertility and 1,000 grain weight, they're the two traits that we feel are really important in assessing the end heat stress tolerance of lines. The other traits of the leaf senescence, they're really important, but for assessing fertility and 1,000 grain weight are the real yield determining traits, so we spent a fair bit of effort analysing them. Here are some common varieties that we use regularly in our testing, and show that there is significant variation for both grain size and fertility in the data set, and there are a number of poorer performing lines such as Sunstate, Wild Catcham, Livingston, and Ellison, Halberd, Mace, H45. They all seem to hold up really quite well. So there is significant variation, which gives hope to be able to shift the germplasm in a direction that we want. I also mentioned before that we screen exotic lines, and this graph is just here to simply show that there is potential to find some really interesting material, new genetics out there that we can introgress into current germplasm to hopefully improve performance under heat stress conditions. So the MEF projects, these are field validation of the controlled environment experiments, as I said before. They occur at the three managed environment facilities at Merredin, Yanco and Narrabri, and here we use a delayed sowing time to increase the chance of exposure to hot conditions later in the season. They receive supplementary irrigation to once again hopefully offset any effects of drought. And at Merredin, we have one experiment where we use rain-out shelters to amplify heat stress. So the experiment gets to roughly anthesis, and the heat chamber is put on to amplify the heat experienced by those plants. And we measure very similar traits at these facilities, but with the addition of grain yield to kind of get a better idea, a better handle on how these crops would have gone in field conditions. Some early results. This is a table of results from 2010, I believe, where we had data from all three sites, and it shows the number of days over 32 degrees, so a moderate heat stress event, and at Merredin they had 16 days in excess of 32 degrees. So they had, and this is during the anthesis to early grain field period, so they had quite a lot of heat stress experienced. And even at Narrabri, there was a couple of days, but a lot less. But so in the lower part of that graph, that table, is some of the statistics, and the percent variation is what's quite interesting in this table. And looking at growing season rainfall, the growing season rainfall was quite even at each of the three sites, albeit with 200 millimetres of supplementary irrigation at Merredin, so it was extremely dry in that year. But rainfall accounted for 44% of the variation in the yield data. So as we all know, it's elementary, but rainfall is incredibly important, as illustrated by there, to determine yield of crops. But not far behind it is maximum average temperature post-anthesis, which was responsible for 34% of the variation. Less than rainfall, but it is as shown there, a very, very important component of determining yield and a very big constraint to yield performance. This graph is the average mean grain yield from the whole experiment over 2010 and 2011, mapped by the average maximum temperature for the anthesis early grain fill period, and shows a very strong linear decline in yield as a response to average maximum temperature. And yeah, it illustrates the very strong negative effect that heat has on the yield achieved. And with coming year's data sets, we hope to improve this correlation, add data points to it, and also hopefully produce a line or a curve for individual genotypes to map their response to average maximum temperature and field conditions as well, to get a better handle on individual variety performance. So the next phase for these projects is to include more mapping populations to genetically dissect heat stress tolerance, in the hope of identifying QTLs and eventually markers which can be used for screening in breeding programs. And a big component of it is also to continue screening exotic introductions and to introgress any advantageous genetics that we can find into material that we can then hopefully somewhere down the line deliver varieties with better heat stress performance. But at the moment, the ultimate goal is to identify genetic markers, understand the genetics a bit better behind heat stress tolerance, so we can develop material for the future. So what does this mean for now? As I showed before, there is significant variation between variety responses. It's our feeling at the moment that varieties from the southern region that are better adapted to the southern region are generally a bit more heat stress tolerant. So things like gladius and mace. And gladius is interesting given that it came from another project specifically designed to develop drought stress tolerance in wheat. So that's something else we're investigating, hopefully trying to identify some tie-ups between drought and stress genetically when we've got some more information on the genetics of heat stress. But the real take-home message for you agronomists is that heat stress tolerance is important, but it's still a secondary trait when selecting varieties. Varieties should really still be selected on general agronomic adaptation, diseases, maturity, and the maturity thing is important because agronomic best practices at the moment, selecting your varieties to flower in an appropriate time and making sure it doesn't flower too late will reduce the impact of heat stress. So that's the real take-home message from me today. So thank you very much, and I'll hand over to Tim.
Thanks, Paul.